In the following series of videos, we are going to talk about intermolecular forces. This is when our molecules that we studied in Chemistry 161 are close to one another. How are they actually going to interact? Because we talked about bonding internally within a molecule is based on the attraction between opposite charges and the repelling of like charges. Well, that same set of forces is going to affect how molecules themselves then interact over then a larger distance. And so we're going to call these interactions intermolecular forces. And we find that within a sample of a pure compound, which will be the focus of this chapter, those intermolecular forces dictate the physical properties of compounds to a large extent. And so we'll talk through those different physical properties and we'll talk about how they change and how those intermolecular forces between the molecules affect that change. Let's start with just an overview of the states of matter and the phase changes before we dive in any deeper. So, hopefully, this is familiar or something like it. Just the states of matter. We are used to hearing about solid, liquid, and gas. Later on, we'll talk about also supercritical fluids. By way of overview, let's remind ourselves the difference between these different states of matter. So we have solids, which will be very low kinetic energy versions of a compound. It means that there's not a lot of movement. There's not translational movement of particles through space. Instead, they're vibrating and maybe twisting and turning. And stretching, but in a stationary position relative to other molecules or particles. And so that is going to give most of our solids then a higher density than a liquid or a gas. And it's going to give it a rigid shape that doesn't change in a definite volume. Now, as we go from solid to liquid, the amount of kinetic energy that the average particle has overall increases. And kinetic energy is really that measure of motion, the amount of energy in the movement of the particles. So they might stretch and bend and twist and shake and vibrate more. But they will also start moving around. So they'll have translational motion. Now, our particles are still very close together. And I like to imagine them as just like tumbling all over one another. So we've increased the amount of kinetic energy. We're seeing an increase in motion, and so we're going to see usually a decrease in density as they are moving around so much. They'll be a little further apart. Um, and we see too in this state because of that while our volume will remain fixed, the shape of it won't, and it'll take on the shape of any container you put that liquid in. Now, if you input even more energy in terms of kinetic energy into that liquid, you're going to end up with a gas. And now these particles are vibrating and shaking and rotating, but they're also moving very rapidly through space. So their translational motion is increased. And so they're zipping all around until they hit a wall, and then they bounce, and then they go hit another wall and they bounce back. And in this case, then our density gets very low because there's becomes more space in between our particles as they're moving around so quickly. There also is no shape to a gas and there's no definite volume. It'll occupy whatever space you put it in, any container you put it in. So it doesn't have that shape or that volume that we would see for a solid. Now, we're going to talk about the relative strength of intermolecular forces in these different phases of matter. And we'll see that intermolecular forces will be relatively strong in a solid and weak in a gas state phase. And we'll talk about that in more detail. One thing that we haven't mentioned yet about solid states that I'll take a quick moment with here is that they have kind of two different kinds that we commonly see. Crystalline solids, which are highly ordered and will arrange themselves in a very specific pattern that is consistent through the whole solid. And you get these beautiful crystal structures. And we'll talk a lot about that in Chemistry 163. And then we also have amorphous solids that usually come about when the solid forms really rapidly, like if something cools very quickly, like in this case, obsidian or like lava cools quickly to form a rock. And we get these amorphous solids that have less order to them. And so our particles aren't in the same perfect pattern that's repeating throughout the entire solid. There's also a lot of times impurities embedded within these solids. Sometimes, rather than just cooling, it's really large molecules form a solid and they kind of get tangled along the way. And that creates this irregularity in the structure of the solid. So that felt like a little bit of a tangent. Because now I want to talk about phase changes. I'm going to quick review. So these should hopefully look familiar when we talked about matter in our previous class in the fall. But if we have solid, liquid, and gas states, then we have phase transitions that occur as a solid becomes a liquid becomes a gas, or the other way around, a gas becomes a liquid, becomes a solid. The names for these are listed here on this slide. And in green, I'm showing all of our phase transitions that occur where we go from a substance that has a lower amount of kinetic energy to one that has a higher amount of kinetic energy. In all of these cases, we have to input energy into the system. So those particles, which aren't moving very much, can have enough energy to move all around. And so this is inherently an endothermic process, and that we will need energy or heat or kinetic energy to increase within our system. And so it needs to absorb it from its surroundings. So as that happens, if we have a solid, it'll become a liquid, meaning it moves around more. It absorbed energy and it's moving around. Now it's a liquid. That phase transition we refer to as fusion. Now, you probably don't call it that when it happens in a glass of water with a piece of ice in it. Probably call it melting, right? And melting is fine. But when you see the word fusion, it means melting. Now, as you go from a liquid to a gas, as you input more of that energy into the system, as it absorbs it from its surroundings, then we have what's called vaporization or evaporation. And that's when we see our liquid particles become a gas and they kind of break off from that liquid that's bound close together and they start zipping all over the place. Now, thinking about this in the reverse, phase transitions that go from gas to liquid to solid. In these cases, we're taking molecules that have a lot of kinetic energy and we're slowing them down. And so they can rest, settle next to each other, and stay stationary, but still vibrating in the solid state. So in these cases, the particles have to get rid of energy to slow down. And so it's an exothermic process. That system of particles releases energy into the surroundings. It like sheds it, it gets rid of it. And so our phase transitions that go from gas to liquid and liquid to solid are going to be exothermic processes. The surroundings will get hotter. So when we go from a gas to a liquid, we call this condensation. And when we go from a liquid to a solid, we call this freezing. For some reason, these terms are more intuitive than our endothermic counterpoints for some reason to me. I grew up with the word freezing. Maybe that was just me. But yes, get used to the language of these phase transitions. Now, we do have cases where a solid becomes a gas without ever being a liquid, or a gas becomes a solid without ever going through that liquid phase. So these transitions have another name. They are called deposition when we have an exothermic process where a gas is slowing down and becoming a solid. And we have sublimation when we see a solid become a gas in an endothermic process. And you see sublimation all of the time, very slowly. In my freezer, I've got some ice cubes that are super old because it's winter. And they are slowly getting smaller and smaller and smaller. Every time I open the freezer door, the ice cubes are a little bit smaller in their tray. And if I leave them there long enough, they will completely sublime. Now, they never melt because it's in my freezer. It's super cold. But some of those particles will have enough kinetic energy to become the gas phase, and then they'll just kind of drift away into my freezer and then probably become ice somewhere else. So here are our phase transitions. In the next set of lectures, we're going to focus on intermolecular forces and then apply that knowledge to these phase transitions where we have fusion or melting and vaporization or boiling that we'll be looking at along with other physical properties.